something to the chat.
Yes, it's some links that I'll be talking about.
Okay,
There they go.
cool.
How's everyone?
Everyone.
Doing good. How you guys doing?
Where is everyone?
Yeah,
Everyone's good.
we're doing pretty good for a Monday. We got a little life.
Yeah,
Yeah, we just did check in and we got a little bit of life in here, so we're doing all right.
awesome. How many are we today?
Longer than I'm good.
How many are we? We are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. 11.
Hey, we see everyone?
Okay, perfect. Any questions to start with, or should I just start in?
No, does anyone have any questions? Oh, Jace has a question for you.
Okay.
Go ahead, nice and loud, Jace.
What do you think of the multiverse theory?
When I first heard it, I thought, yes, this sounds awesome, because it puts the sort of the explanation of the beginning of the universe one step back. So we have a bit of, it doesn't explain our universe, but it does kind of possibly explain something. The problem with the multiverse is it is probably a non-testable theory. So it's not going to be, it can't be called a theory because we cannot test it. By definition, everything that we know of is within our universe and is not connected to anything outside our universe. So
Unless we can find a way to bridge the gap.
bridge the gap, yeah. String theory has some bridging there with brains and brains touching and things like that. I kind of like the image of a bathtub full of bubbles and each one is a universe. That kind of certainly would increase the population of intelligent beings.
Weird.
Cool. Jake, what was it you were talking about the other day about, no, the opposite, right? Just by looking at something, by the observer, you change it. What was that?
Oh, yeah, observing something can change what you observe.
Is that the Heisenberg principle?
I think it is.
Is that, yeah, no, it was looking at whether or not light was a wave or a particle.
Okay, that's different.
Yeah, that's something else.
That depends on how you test light. If you test it to see if it's a particle, it will be a particle. And if you test it to be a wave, it will show as a wave. The Heisenberg principle is that you cannot know the position and velocity of anything at the same time. And that the simple act of observing something changes the particle. And that's why we can never get to absolute zero, where all motion stops, because then we would know the position and the velocity of a particle, and that is not possible. Just like, you can get really close to the speed of light but never get there, you can get really close to absolute zero but never get there also.
Huh.
Kelvin, not
Yeah.
Celsius.
Cool. Any other questions?
Are you sure?
All right, we are ready.
Okay, let me share my screen.
Oh wait, I better enable you. Sorry,
Oh, yep.
I'm out of practice. Oh hey, I was going to tell you. Next month we have. I heard this lady on CBC chatting, Louise Edwards, and she's studies galaxies down at a university down in California.
Yeah.
And she's going to be joining us. So I'd invite you.
Oh, awesome. I would love to sit on that. Yes.
Yeah, she was on CBC radio, and actually, if you search her up, Louise, I'll send you the link.
Okay.
She sounded just lovely, and I sent her a message, and she's like, "Yeah, sure."
Awesome. Yeah. I've got my next month. I've got just about every day. I've got a Zoom thing with some group around the world talking about something. So now is certainly the time for expanding our knowledge. That's for sure.
Yeah, cool.
Okay, let's go there. And okay. So this is going to be kind of an overview of the universe. I'm just trying to get minimize my, there we go. And in the chat, these are the links I've sent just for interest's sake. This is the sky in 2020. One of our members, her husband builds extremely good telescopes, and she does astrophotography. So she put together about a 3-minute video of some of her shots from 2020. And it's an amazing video to watch. It only takes 3 seconds. So there you go. Another one of our members, actually, he's a Toronto member, but belongs to the RASC, has just written a book called Not Yet Imagined. So all about the Hubble Space Telescope, and it's a free download. So I've added that link. And this is really fun to watch. It's an astronomy picture of the day, and it shows all the moon phases for 2021. So it'll show you sort of the alignment of the moon and the Earth. It'll show you the moon actually kind of tips and tilts a bit. It'll show you that as the terminator, that line between the day and the night on the moon comes across the moon. It'll show you all the craters that are there. And then this line in the distance is how far away from the Earth the moon is at any one time. Of course, elliptical orbit, sometimes it's closer, sometimes it's farther, but it's always right around 30, and the units here are Earth diameters. So about 30 Earth diameters is where the moon orbits. So those are just for a little bit of fun. So what I'm going to talk today is the universe in 11 steps. It's kind of an overview of the whole universe. And we're going to start with the Earth in, pretend it's in an imaginary cube, which is just slightly larger than the planet itself. And most people can kind of imagine this kind of cube. You can kind of grasp the dimensions. It's certainly easy to fly around, you know, quarter of the Earth in a few hours. So the Earth is 12,742 kilometers across. And now in the following slides, each cube is going to multiply. So the width, the depth, and the height is going to be 100 times bigger. And so the volume is going to be 1,000,000 times bigger. So that's step one. Step two, the Earth is now reduced to a dot right there. This cube easily holds the moon's orbit, which is almost 800,000 kilometers across. And like I said, the Earth-Moon distance is almost exactly 30 diameters. It does vary a little bit. And it's another easily, a modest leap for mankind. It takes about 2.5 days to go from the Earth to the moon for a person. And spacecraft, or interplanetary spacecraft, telescopes, robotic missions, that sort of thing, they're not big squishy bags of fluid. So they can go much, much faster and get to the moon in about 6 hours. So we have a 2 million kilometer cube, which is about 5 light seconds across. And I have kind of a challenge for anybody. It takes the moon 27 1/3 days to orbit the Earth. However, from new moon to new moon, or pick any phase, full moon to full moon, takes 29 days. And I want to see if anybody can come up with the reason for that. And next week we'll go over that and look at the answer. The diameter of the moon is just under 3,500 kilometers. And the mass of the moon is just 1% of the Earth. So now, expanding the cube. Step 3 takes in portions of the orbits of Mercury, Venus, and Mars. And this width is just a little bit larger than what's become a standard cosmic measuring unit, or the astronomical unit, which is the average distance of the distance between the sun and the earth, about 150 million kilometers. And you'll hear a lot of things mentioned in AUs, or astronomical units. So dozens of spacecraft have passed through this area, but it's essentially empty space, except for a few thousand asteroids that have drifted in from the asteroid belt, and the occasional comet. So now we have a 200 million kilometers on each side of this cube, with an 11.2 light minute distance. And I do have a bunch of facts, just in case anybody asks me about orbital periods of planets and stuff like that. But I think for now, we'll just keep going out. Our step, oh, right, I showed this before. So we saw in here, we see orbits of Mercury, Venus, Earth, and Mars. And it looks like most of the time, the Earth would be closest to Venus. But if you look, here we have the Sun, Mercury, Venus, Earth, and Mars. And from the Earth is a line that will go to the closest planet to it at any one time. And if you look over several years, you'll see that about 50% of the time, Mercury is actually closest to the Earth, followed by about a third of the time with Venus, and just over 10% of the time for Mars. And this actually goes for all the other outer planets also. So Mercury is closest to any planet more often than any other planet is closest to that planet. Little confusing there, but it's kind of the thing you can trick people with. So our step 4, now we have included all the planets and Pluto. The only solar system members outside of this cube would be comets. And from this vantage point, if we were here in space, we would only just barely be able to see Jupiter and Saturn. The sun itself is the only object of significance in our solar system. The planets are kind of merely debris. So if I give you 1,000 grains of sand and I wanted you to distribute them between the sun, the planets, the asteroids, and all the comets, so 998 would go into making the sun, 1 would go into Jupiter, and the last grain of sand would take care of everything else, all the asteroids, all the other planets, and all the comets. So basically our solar system is the sun, and maybe a little bit of Jupiter in there too. So we now have a 20 billion kilometer cube with a light time of 17 hours. Moving on to step 5. What you're seeing here is a cube which encloses mostly empty space. The sun would appear as a very bright star. And this haze that you kind of see around the sun is from the Oort cloud, which are billions of comets right at the fringe of our solar system. The nearest star is still 50 times further away than this 2 billion kilometer cube. And light time is now 70 light days. We can start thinking of light time as also seeing into the past. Whatever we see at this distance happened 70 days ago. That's step 5. What else? The estimated number of comets inside this cube would be 100 billion, with the average diameter of a comet being about 2 kilometers. The estimated total mass of all the known comets is just 100 times Earth mass. So billions of comets, but again, the mass of our solar system is in the sun and Jupiter.
Colleen, where did the comets come from? Like where you see the Oort cloud there, like where did it originate?
That they formed as the solar system was forming. And I'd like to do a talk about stellar evolution, and that will include how the comets came to be.
Okay.
So for right now, from the formation of the solar system. Okay, step 6. We are now 20 light years across, and there are about 17 stars in this cube. There's 8 single stars, 3 double stars, and 1 triple star. So actually, most of the stars that we see are in binary, double star systems, or even up to 6 stars, all gravitationally bound. Our sun being a single star is actually an anomaly as far as stars go. So our nearest star is Proxima Centauri, and that's 8,000 times farther away than Neptune. And we are just starting to really see the amazing distances in the universe. If the sun were the size of a grapefruit, this cube would have to be larger than Earth to provide the correct scale. So sun the size of a grapefruit to enclose this many stars, a huge, huge cube. Now our sun is much brighter than the average stars. The majority of stars in the sky are dim suns called red dwarfs or M dwarfs. The only star in this cube that is significantly brighter than the sun is Sirius down here. That's the brightest star in our sky. It's bright because not only is it intrinsically bright, but it's also very close. It's not quite 9 light years away. So each star here has an enormous amount of empty space around it. If you can think of about 400 cubic light years, so an enormous amount of empty space. Although it is not a total vacuum, but it is very close. On Earth at sea level, there are, if you think of the size of a sugar cube, the air contained in there would be 10 quadrillion particles in that at Earth and sea level. In this kind of space, it's not quite a vacuum. There is only 1 atom per that little cubic centimeter. So not quite total vacuum yet, but really getting close. So again, 200 trillion kilometers across and about 20 light years. Moving out a bit further. So now we've got a cube with each side of 2,000 light years across, and enclosed in this cube would be about 2 million stars. Now they do seem crowded. Looks like they're very close together, but remember the average distance between stars is about 4 light years. So, and you have to think of this as being 3-dimensional. Shown here are some of the naked eye objects that we can view from Earth, including these bright stars, Deneb, Spica, Betelgeuse, and Rigel. The Orion Nebula, which is the closest star-producing area to Earth. It's about 1,500 light years away. And I'm sure you've all seen the Pleiades star cluster, beautiful little star cluster in Taurus. So what else there? So again, the volume of this cube now is 8 billion cubic light years, and it has 2 million stars in it. And so these are our closest stars and deep sky objects. And now we are out to 200,000 light years across our cube, and it spans the whole Milky Way. Milky Way galaxy is about 100,000 light years across and about 3,000 light years thick, and contains about 200 billion stars. So you can see that our sun is about 2/3 of the way out. I don't have my laser. There we go. I love the laser. Our sun is about 2/3 of the way out from the center of the Milky Way. We orbit the Milky Way going in and out of the spiral arms, and it takes about 220 million years to complete an orbit. So we've gone around about 20, 25 times since our sun became a sun and a solar system. And we can also start seeing some of the dwarf galaxies that orbit our Milky Way galaxy. We've got the large and the small Magellanic Clouds. Those are only seen from the southern hemisphere, and there's lots of other dwarf galaxies. It's estimated that the Milky Way has actually devoured about 13 dwarf galaxies in its lifetime, because we are the heavier, more massive, more gravity, so we're pulling in these little dwarf galaxies. The estimated number of stars in this whole picture, the Milky Way galaxy, all the dwarf galaxies, etc., is about, oh shoot, I lost my page, about 1 trillion stars that we're looking at here. One more step out, and our cube is now 20 million light years across. And the Milky Way we see is just one of several dozens of galaxies. Now the galaxies within about 3 million light years are gravitationally bound, and that is called our local group. The Andromeda galaxy, we see right there, is the largest of the group. And here, remember, talking about vacuum. So last we left the vacuum, it was 1 atom per cubic centimeter. We now have in this kind of space 1 atom per cubic meter. So this is almost a perfect vacuum. And there are, in this cube, there would be about 6 major spiral galaxies. And we see 2 up here, and we have these 3, and there's a couple more down there. So 5, 6 or 7 major spiral galaxies, about 100 minor spirals and dwarf galaxies, and an estimated 10 trillion stars that we are looking at here. One more step out, and we are looking at a cube with a size of 2 billion light years across. And this is where we see galaxy clusters and superclusters. So we saw our local group of our Milky Way and Andromeda. So we have a little galaxy cluster there. The little galaxy clusters make bigger galaxy clusters, and there's even some larger structure called superclusters. There's probably 100 million galaxies that we're looking at right here, with a few trillion stars. The average distance between the galaxy superclusters is about 300 million light years. And the largest known galaxy supercluster holds 100,000 galaxies. So we have our little local group right in here, part of the Virgo cluster. Then we have our local supercluster, and then we have other superclusters. And the names come from the constellations that they're in. Now remember, they're not close to Earth. These are billions of light years away, but we still see them within our constellations. So one of the largest structures in the universe is our local supercluster. Now here, if we see, here's our Milky Way galaxy, and every dot you see here is a galaxy. And these lines that are flowing from the dots show the actual motion of those galaxies. We're looking at about 520 million light years across. And we can see that all these galaxies are kind of moving in towards each other. And then we have these other superclusters where other sort of centers of gravity are, and the galaxies are moving towards them. So we got the Coma cluster, Shapley, and the Perseus Pisces cluster, supercluster.
So
Sorry.
even at like this grand of a scale, like gravity is just super important in doing all kinds of things.
Gravity, yes, gravity reaches out forever and is always an attractive force. So gravity kind of holds the superclusters together, yeah. And our last step, and now we are looking at a cube that is greater than the known universe. The estimate number of galaxies here is 2 trillion galaxies. The estimated number of stars in the universe is 400 quintillion stars. And the estimated number of planets is about 1 trillion per galaxy. So we know the universe is 13.77 billion years old. And again, we can see this as this image looking at time instead of distances. We see present is right there, so that's where we are, and everything we look close to us, we are all at the present time. Recent time can be, you know, a little ways out from us. And then the farthest back in time that we can see is 380,000 years after the Big Bang. And this is where the cosmic microwave background radiation stops us looking any further. It's when the universe became, before that time, the universe was opaque, so light couldn't move around anywhere. After that time, it became transparent and the universe could expand, and this light has been slowly expanding also. And it's, as you expand things, you get cooler. And that's their background temperature in the universe is about 2.73 degrees above absolute zero. So we can't see anything farther back than this red circle, but we know before that, that's when the Big Bang happened. And by using our knowledge of high energy physics, we can deduce what occurred. So there was an event that caused the universe to inflate very rapidly for a very short period of time. And then the universe continued expanding at an ever slower acceleration until about 6 to 7 billion years ago. Then the universe started expanding again, and its expanding acceleration is increasing. The universe is now expanding faster than it ever did in the past. So possibly the eventual destiny of the universe kind of seems to be this continual expansion, perhaps forever. The galaxy clusters will separate from each other. Then the galaxies, the stars will end their lives and be pushed apart from each other. And then the stellar remnants will expand. Eventually, even atoms will succumb to this expansion, and the whole universe will be dark and cold and empty. But that's not going to happen for trillions and trillions and trillions of years. And that's all because of dark energy, which is a whole talk in itself, but I'll just mention that now. So it looks bleak, but again, nothing that's happening soon. So we can still enjoy the wonders of the universe our whole lifetime. And oh, I didn't have an end page there. That is all for today.
Yeah, woo!
Now, I'm sure you might have a question or two or just be blown away.
Yeah, definitely mind-boggling. Here, let's we get some lights on here so you can see us a little bit, Colleen, and we can ask some questions.
Okay.
There we are. right, let's start over. Casey, what'd you think, buddy?
I really like the sand demonstration you used with the sand pebbles, and I also really like the I forget what you call it, the thing that was apparently bigger than the universe.
Yeah, that final step, yeah.
But and then the last one where I always wondered like what would happen if atoms were farther from each other, like if things would be weaker or bigger and stuff.
Yeah, dark energy could eventually push everything apart. We know particles have half-lives, you know, the time it takes for them to kind of decay. A neutron, if you have a neutron sitting out in space, in about 15 minutes, it will become a proton and electron. We have no idea how long it takes protons to decay, unfortunately. We don't think there's probably been a proton decay since the universe began. But over you know, we're only talking billions of years for the universe now. Over trillions, it's probably the protons will probably decay, and because of dark energy and just they're made out of quarks. I'm not sure, quarks are never found alone, so what exactly is going to happen when protons decay, but the universe will eventually just be dark and cold.
Cool. Will?
My brain is like literally going to explode.
Yes,
Success.
success, absolutely.
Yeah. The universe is big, very big. Yeah.
Yes,
And so empty.
yeah, basically space is empty.
Jace, what'd you think?
From what I saw of it, I had to step up for a minute. It was big.
Yeah.
But almost comprehensible. You know, if we take it step by step, we can almost comprehend how big it is.
Yeah, no, I like that aspect of it, right?
Yeah.
Dill?
I liked it a lot. I liked the sugar cube one. That part of it I really liked.
Yeah, that was a really good analogy, I think, for making sense of the sugar cube and then
Oh, yeah.
grains of sand. Yeah, that was Dill liked that one. Jared? He said he was confused, but he liked it.
Another success. If I can confuse people and want them then to find out why they are confused,
Yeah.
works for me.
Lucy,
Hi,
what did you think?
I think scary.
Sorry, I didn't catch that.
I asked her what she thought, and she says, "I think it's scary."
Not scary, nothing we can do about it. So we're just going to live our life and observe.
Observe and try to understand, right? All right, Newman.
Yeah, good refresher. I kind of like had done a bit of this with the Great Attractor and everything.
Right.
Superclusters and a
Yeah.
supercluster of a supercluster is what drag to is most likely what it is, kind of thing. But yeah, it's really cool. And then also, I was looking because you were talking about parsecs and everything. I was like, okay, well, how big is a parsec in kilometers? Oh, it's a lot because it's trillion. And
Yeah.
how far away is Andromeda? Is 770,000 parsecs, kind of thing.
Yeah, yeah.
I was looking into how long it would take to travel there, and at the speed if we were going to the moon, that was 3,000 kilometers ish. Now,
Yeah.
if we went that speed traveling to Andromeda, it would take us something like 500 trillion years.
Yeah, I just watched a really interesting YouTube talking about space travel. And if you could get a rocket ship and have enough fuel to continually accelerate, so every second you're going faster and faster and faster, it would only take you maybe 25 years to get to Andromeda.
Yeah.
However, you can't come back because millions of years would have passed for the Earth. And we kind of did that one time talking about time travel and stuff. So yeah, acceleration in gravity, and you know, we could travel through the universe if we could get an infinite supply of things to keep us accelerating.
An infinite supply of fuel. If only we had that.
Oh yeah, that's going to be the toughie.
Yeah.
The closest thing we have is solar energy.
Yeah. Well, anyway. Yeah.
Solar energy is great if you're in a solar system.
Yeah, that's the thing.
Right. I guess in that vastness, there'd be all kinds of, yeah, no. Huh.
If you're between stars or between galaxies,
And you run out of gas.
yeah, you're in trouble.
Yeah.
Yeah.
Jake, what'd you think, man?
I thought it was really cool. Over the Christmas oh yeah, I just realized this is the first time we've chatted.
Yes, yes.
Happy New Year.
Happy
During or for Christmas, I got a book, and you might know of it. It's called Astrophysics for People in a Hurry.
Yes,
Neil deGrasse Tyson. And I
yes.
absolutely loved the book.
Good.
I sent it to one of the other science teachers in the school, but it talked a lot about like a lot of the stuff that you mentioned is stuff that was in the book. I mean, it's right behind you.
I've got that book somewhere too. Yeah.
And I thought it was really interesting because just some of the parallels that you see, and a lot of the information was the same from the book and what you were talking about. So being able to grasp it was a lot easier. But
Yeah, we all get our facts from the same place.
yeah, but yeah, it was just a really interesting thing to listen to. I thought, hey, I know that because I read this book.
That's good. That's good. Yeah. It's like learning a new language. You hear the terms and finally they, you know, if you hear them enough, they start making sense.
Yeah, last week you weren't when you weren't here. We did was it last week or the week before?
Last week.
I was talking about dark matter and dark energy and some of that stuff. Just learning that from the book. And now I'm reading a book. It's called, what was it, The Invisible Spoon or something like that.
Oh, I hadn't heard that one.
Talking about the different elements and the story behind them. But yeah.
Good. Excellent.
Cool. Conrad, what about you, buddy?
My name's Conrad. I thought it was good.
You liked it? Yeah. Brent at the back.
Yeah, it was definitely mind-blowing. At the beginning, I really liked the little cube and how everything was contained, and then just one little step back. But then all of a sudden, you're like so far away that it is just mind-boggling to imagine things in that
Yeah.
size. So
Yeah. We
but,
don't deal with those kind of distances or volumes.
it's you lost me after a while.
Okay, I'll get you back.
Yeah, I thought it was great. I thought it was a good way to kind of to look at it and then, yeah, to keep taking a step back. But you mentioned when you were talking about the universe formation, and it was slowing down, or it was slowing down to about
Yep,
6 billion years,
yep.
and then it started to expand again. And do they have, what are the hypotheses for for why?
That is when dark energy was invoked. And to move the galaxies apart faster and faster, it is estimated that about 75% of the universe is dark energy. About 23% is dark matter. So that's just matter that we know exerts a gravitational influence on things we can see, but does not react anyway with electromagnetic radiation, so it doesn't absorb or emit light, so we can't see it. And that last little, 4% is everything that we kind of know of, all the planets and galaxies and stars, the physical stuff we think of. But even then, most of that is the hydrogen gas between galaxies. So planets and galaxies and stars, the physical stuff we can think of is only like 0.4% of the universe. So we basically know nothing about the universe.
So yeah. So it's like, so something happened 6 billion years ago, and this force that we don't, these forces that we really don't understand, that thinks that that's when it came into existence, was at that time.
Yeah, now, one reason, kind of a simplified version is, so the Big Bang happened and everything expanded outwards in creating space and time. And of course, it's full of mass. So all that mass is trying to attract each other. So that expansion was slowing down. And then it appears that things got far enough apart that the space between things delved into dark energy. Dark energy was allowed to exert itself and push everything apart.
Huh.
That's really simplified.
No, that's good.
But we had no idea about dark energy until the 1990s, so like 25 years ago. Before that, the big questions in cosmology was this expansion going to just keep slowing down forever and ever? Or was it going to, I can see Jake back there. Yes, yes. Was that the mass enough that it would stop expansion and then come back together into a big crunch? So those were the basic things that people were trying to understand. And in the 1990s, two different groups started looking to see which one it would happen. And they found a third alternative. They found that everything was actually expanding faster and faster away from each other. So dark energy came right out of left field.
Huh. And now, and this was 1995, and now we
Yep.
now know that this dark energy that we didn't know about, it makes up this much of the universe.
75% of the universe, yeah.
Wow. What else
Yeah.
do you know, hey? Wow, cool. Any other questions or comments, gang? Oh,
Of course, you mentioned that, and I wanted to mention omega and lambda. The what was it? The cosmological constant to figure out that stuff. And
Yeah.
it talked about it in the book, but I haven't quite been able to understand how that worked, because when I looked it up, they combined the two into what was it, like a cosmological ratio or something like that, or
Yeah. They start combining things and stuff, and it gets, yeah. Omega is kind of like the total energy mass of the universe. And looking at the Hubble constant and things, if the universe was a closed universe, then there's enough mass that it would pull together. If it's an open universe, there's enough, the dark energy would overwhelm things and just take off. The closer to one, I'm hoping I'm saying this right. It's been a while since I've looked at omega. The closer to one, it means that we have a flat universe, and that doesn't talk about actual shape. It talks about the expansion, and we seem to be really close to one, which includes dark energy, dark matter, and normal matter.
yeah,
So we will just keep expanding. Yes.
because when they tried to find what omega was, they couldn't even get close enough to get to one, and then they thought, well, what about this other? What about this?
Yeah.
They introduced dark matter and dark energy, and it was able to bump it up close enough. But
And it also had to include inflation at the beginning of the Big Bang.
well, that's why I mentioned lambda, because that's what Einstein had mentioned.
Yeah.
Einstein didn't like lambda. He said that it was
His biggest mistake.
his mistake. That's what it was.
Yeah.
That the lambda makes in an equation, it makes the universe stand still.
Yeah.
And then
He thought
and
he and a bunch of other astronomers thought the universe was static. It always has been, and it always will be exactly as it is. So when his equations saw that it had to be either expanding or contracting, he threw in lambda, but he never liked it. And it turns out it's exactly what was needed. Yeah.
Yeah. I also wanted to mention that the other thing about what was it, dark matter.
Mm-hmm.
Matter creating gravity, like with gravity, but it doesn't interact with anything. And there was a sentence in the book on whether gravity and matter actually do need to be together. If matter actually does stay with gravity and gravity stay with matter, or if they're two separate things that most of the time react or interact with each other, but if they actually don't have to. And I thought that was an interesting sentence. Just one sentence that just threw everything out the window.
Yeah, there's that too. Yeah, and we do not know what gives mass to objects. There's, the Higgs boson and all that, the whole separate thing. But yeah, so we don't understand gravity because we don't know how objects have mass to then warp space-time with gravity.
Yeah, and then that's going into the Newton and Einstein's theory on what
Yes.
gravity is.
Yeah.
Yeah.
Rob, you look.
No, I'm back to thinking about thinking about what gives something mass, right? And again,
Yes.
in our science room, we had learned about, what gives something mass would be, the neutrons and the protons and the nucleus. And then it's kind of like, okay, well, like, no, maybe that's not what gives it mass. So like,
It's not.
no, yeah. So what are we doing? What am I teaching people that for?
So because if you started with the heavy stuff, nobody would understand. So a proton is actually mostly empty space with 3 quarks in it. And it's the empty space and the virtual particles that tend to give it mass. However, it has to react with the Higgs boson in the Higgs field.
Yeah. Wow.
Yes.
Well, that's good. That's a lot to think about, Colleen.
Good. For next week, I was thinking of doing something a little bit more practical. There are 3 spacecraft getting to Mars next month. So I thought talk about Mars and past space probes and what we know about Mars now and what we hope to find with these 3 new spacecraft up there. If that would be good.
That sounds pretty great. Oh yeah, we might not be here next week. I'll send you an email. We'll sort it all out.
Sure.
That sounds awesome. All right, Colleen, thank you very much. That was
You're very welcome. Happy New Year
Yeah, happy
to
New
everyone.
Okay,
And thank you again. Thank you.
Bye.
Bye now.
Bye. Thank you.
Rob,
Hello.
you need to organize an afternoon call between Jacob and Colleen. Give them just an hour to talk to each other.
Nerd.
It's nice having someone who understands what I'm